DotMotif, an open-source tool for connectome, subgraph, isomorphism search, and graph queries. Jordan K. Matelsky, Elizabeth P. Reilly, Erik C. Johnson, Jennifer Stiso, Danielle S. Bassett, Brock A. Wester and William Gray-Roncal. Scientific Reports 11, article number 13,045, 2021. Cite this article. 7,217 accesses, 15 citations, 10 Altmetric. Metrics. Abstract. Recent advances in neuroscience have enabled the exploration of brain structure at the level of individual synaptic connections. These connectomics datasets continue to grow in size and complexity. Methods to search for and identify interesting graph patterns offer a promising approach to quickly reduce data dimensionality and enable discovery. These graphs are often too large to be analyzed manually, presenting significant barriers to searching for structure and testing hypotheses. We combine graph database and analysis libraries with an easy-to-use neuroscience grammar suitable for rapidly constructing queries and searching for subgraphs and patterns of interest. Our approach abstracts many of the computer science and graph theory challenges associated with nanoscale brain network analysis and allows scientists to quickly conduct research at scale. We demonstrate the utility of these tools by searching for motifs on simulated data and real public connectomics datasets, and we share simple and complex structures relevant to the neuroscience community. We contextualize our findings and provide case studies and software to motivate future neuroscience exploration. Similar content being viewed by others. Edge-colored directed subgraph enumeration on the connectome. Article Open Access July 5, 2022. Towards a biologically annotated brain connectome. Article October 17, 2023. Brain Taco, an explorable multiscale multimodal brain transcriptomic and connectivity data resource. Article Open Access June 14, 2024. Introduction. Modern nanoscale connectomics research commonly involves the conversion of microscopy imagery data into a graph representation of connectivity, where nodes represent neurons and directed edges represent the synapses between them one. This process enables researchers to convert terabytes or even petabytes of imagery into megabytes or gigabytes of graph data. Conversion to a network format reduces the cost and complexity of interrogating the data, at the expense of losing information about cellular morphology too. 3. Though this graph representation uses substantially less storage space on disk, answering even seemingly simple network questions, e.g., identifying local graph structure around a particular neuron, or comparing the downstream targets of a certain cell type, may still exceed the computational power, timelines, and budgets available to many research teams, due to the exponential nature of many graph algorithms. 4, 5. This issue is often ameliorated by including node or edge attribute constraints in the search, though this places an additional limitation on the types of questions that a researcher can expect to ask of a connectome dataset. Connectomics researchers have begun to address these challenges of large-scale graph analysis by adopting existing large-scale graph management software from other domains, such as graph databases, and by enforcing consistent, well-architected data schemas. 6, 7. These systems provide performant and cost-effective ways to manipulate larger-than-memory graphs, but tend to require familiarity with complex and nuanced graph query programming languages such as Gremlin or Cypher. Though graph databases continue to grow in popularity, the expertise to administer or use these technologies is still not common in the biological sciences. In order to make the study of connectomes accessible and computationally efficient, we developed DotMotif, an intuitive but powerful graph tool designed to reduce the expertise and time required to begin interrogating biological graphs of any size. DotMotif acts as an interface to common graph management systems such as the NetworkX Python library or the Neo4j graph database. abstracting the intricacies of subgraph query design and enabling researchers to focus on field-specific scientific inquiry. DotMotif assists researchers in query design by exposing an intuitive, simple syntax that automatically validates and optimizes user queries and adapts to different graph tool backends without the need for additional user input. We present the DotMotif Python package and software architecture, which enables researchers to write queries while remaining agnostic to underlying technologies. We demonstrate DotMotif's utility by assessing its advantages over manual query design, and we share several use cases inspired by ongoing research in the connectomics community. We also share examples of how these findings might inform future work, including efforts to design better local connectivity rule sets, establish expected motif prevalence, and produce better generative models of a connectome for evaluation, null model design, or for comparison across species, brain region, and modality. Background. Figure 1. Subgraph search. Subgraph search is formally defined in background section. A motif query is defined. In this example, the query is a simple directed triangle. One edge, red, has been assigned an attribute constraint, perhaps a neurotransmitter type or weight threshold. Be a directed search graph or host graph. Two edges in the host graph share the same attribute as the constrained edge in the motif. C. The motif is discovered in the search graph. Two unique detections are shown here, highlighted in yellow and green. Note that edges and nodes in the host graph may appear in more than one mapping. Full-size image. Many of the fundamental questions of modern neuroscience rely on the study of simple circuits of neural connectivity in the brain. These simple circuits are hypothesized to be repeated and reused many times to perform a similar role. Though they might comprise only a small number of neurons, as shown in Figure 1, these simple circuits or graph motifs may be critical to understanding the functional role of larger structures in the brain, such as cortical columns or other modules of computational importance 8, 9, 10. Due to the nature of available high-resolution imaging modalities, such as electron microscopy, it is not always feasible to collect functional as well as anatomical data at synaptic resolution. In this work, we define motifs as repeating subgraphs, but do not make assumptions about their computational significance. That is, we consider a motif to be any commonly used network architecture, 11, or recurring, significant pattern of interconnections 12. Even if that subgraph structure has unknown computational properties. Identifying these motifs is one motivation for the field of connectomics, the study of the brain through the lens of its connectivity. Many related research efforts seek to construct graph representations of the brain, commonly represented by the notation, where a graph G is made up of nodes V, representing neurons, optionally directed, edges E, representing synapses between neurons, and arbitrary attributes A, which may be associated with vertices, edges, or the graph as a whole. For example, node attributes might include qualities such as cell type or functional information. Edge attributes might include synapse weight or neurotransmitter type. Graph attributes might include the species or individual from which the connectome was generated. Neuroscience questions may be reformulated as analyses on a graph, and the neuroscientist may add graph theory to the toolbox of strategies with which to understand the brain 8, 13. Such questions include searching for specific subgraph structures, investigating the connectivity of specific neuron cell types or categories, proofreading connectomes for accuracy, and generating summary statistics on the graph as a whole. 3, 10, 14, 15, 16, 17, 18. Many graphs generated by the connectomics community in recent years have spanned multiple gigabytes of hard drive space to 10, rendering conventional graph toolkits, such as the Common Network X Library 19, or its counterparts in other programming languages, underpowered to address the needs of the scientific community. These tools, which often require all graph data to be stored in RAM, would require impractically expensive compute hardware in order to run fully in memory, and would require impractically long timelines in order to run while swapping data from memory to disk. Instead, some Team 6 have opted to leverage out-of-memory tools such as Neo4j7, Cayley 20, or other graph databases 721, which operate on graph data, much like conventional relational databases operate on tabular data. Despite their power, such tools require expertise in specialized query languages such as Cipher or Gremlin, much like relational databases require knowledge of languages such as SQL. Developing or hiring for this sort of domain expertise may be impractical for many neuroscience research laboratories and is independent from the core expertise needed to formulate and test neuroscience hypotheses. The need for computationally efficient, accessible, and intuitive neural graph analysis tools motivates this work. Motif-based connectomics research is an emerging neuroscience subdiscipline. This community currently depends upon closed-form matrix algebra subgraph counting techniques, which are only established for very specific types of motifs, e.g. fully connected motifs or star graphs. More complicated motifs, such as those which include information about cell or synapse types, or those with more topologically interesting graph connectivity, are currently understudied largely due to this technical gap. Existing tools, such as FanMod, MAVisto, and others offer helpful interfaces for biological motif exploration with support for graph attributes, but encounter limitations when searching for arbitrarily large motifs, or when searching in many thousand-node graphs 11, 12, 22, 23. In order to facilitate directed hypothesis testing in large-scale connectomics, the community will need motif search tools that are able to incorporate information about cell types, local morphology, functional and structural data, and other graph, node, and edge attributes, and which scale to arbitrarily large connectome network sizes. Results. For DotMotif to be useful to the neuroscience community, it is important for potential end users to see its practical utility. We share illustrative DotMotif experiments run on a set of publicly available, seminal connectome datasets. We first validate our results by comparing against existing online data, and then share a network analysis result on both partial as well as complete connectomes. Lastly, we share performance benchmarks for graphs of various sizes. Collectively, these results serve to illustrate how our tools enrich the connectomics toolkit. Datasets. Table 1 connectome graphs reviewed in this work. Full-size table. We demonstrate the use of our tool on both near-complete, most or all of the organism's neurons are included in the graph, connectomes as well as on partial connectomes. Here, we compare connectomes of the invertebrate nematode C, elegans 24, 27, the partial connectome of the invertebrate fruit fly from the Howard Hughes Medical Institute Genelia Hemibrain Project 2, and the partial vertebrate mouse visual cortex connectome from the Intelligence Advanced Research Project Activity, IRPA, Machine Intelligence from Cortical Networks, Microns, Project 10, 28, 29. Further dataset details are available in Table 1. These published graphs do not adhere to a particular database schema or storage system, and each has different node and edge attributes. Despite these differences, all three can be analyzed using the techniques we detail here. Tool validation, declarative queries. Figure 2. A comparison of DotMotif query syntax and the equivalent queries when transpiled to Cipher using the Neo4j executor. A simple query to find inputs to Kenyan cells, KC, from the medial antennal lobe tracts, MALT, in the hemibrain dataset. Note that DotMotif comments are notated with the hash character. B. The equivalent query as panel. A. When converted to the Cipher query language for use with new print systems. Even in a small query such as this, DotMotif syntax tends to be more succinct and readable. C. A simple DotMotif query for a repeated pattern with node and edge constraints. The motif includes a macro called big inhibit small, which establishes a connection between two neurons with a type edge attribute of GABA and with radius nodes attribute constraints on both neuron participants. This macro is reused multiple times in the final motif construction in order to avoid repetitive code. DotMotif automatically infers that nodes A and B are isomorphic, i.e. interchangeable, and that C and D are isomorphic. D.motif converts the query in panel C to the cipher code in D. The equivalent cipher query is substantially longer and harder to maintain or edit, even in the case of this quite simple motif. It also requires explicit notation to avoid reporting duplicate motif automorphisms. Full-size image. As a simple first step towards tool validation, we begin by demonstrating the utility of DotMotif in performing declarative queries on a large connectome graph. In order to illustrate compatibility with data stored in the Newprint data format 6, we ran a DotMotif search query on the partial Drosophila melanogaster connectome, dubbed HemiBrain 2. We then validated these results with the Newprint API at Newprint, genelia.org 6. In this example motif query, Figure 2a, we wanted to find all antennal lobe inputs to Kenyan cells with weights within a certain range. We identified 7 instances of this motif, centered around antennal lobe neurons with IDs 191, 718, 8956, 182, 508, 5656, 581, 306, 3239, 188, 716, 3927, 191, 718, 8956, 182, 508, 5656, and 103, 729, 3275. With these references to neurons in the host graph, we were equipped to look for further patterns among these neurons. In order to confirm that the query above returned results that were identical to those obtained from the canonical Newprint server, we validated these results with the equivalent cipher command, fig. 2b, in the Newprint web application. This exercise demonstrates DotMotif can be used to easily convert declarative neuroscience questions into succinct, efficient graph queries. Comparing undirected subgraph searches across connectomes. As an illustration of the minimal configuration requirements of the DotMotif package, we searched the human proofread subgraph from the IRPA Microns Project 10, 28, 29 for all undirected graphs of size, with the ordering taken from the Atlas of Graphs 30, pages 8 to 30. We then counted the number of times each subgraph appeared. For example, we counted all undirected triangles, Atlas of Graphs ID number 7, and discovered that there were 6,894 unique triangle monomorphisms in the Microns graph when ignoring edge direction. There were 123,264 unique undirected rectangle, Atlas of Graphs ID number 16, monomorphisms. The only undirected graph in this set with no occurrences in the Microns graph was motif ID number 208, which was the complete graph of 6 nodes. We published this complete dataset of all motifs and their respective counts for community use. See Supplemental Material 1. To contextualize these results, we calibrated the parameters of 4 simple random graph models, Erdos, Reilly 31, Undirected Geometric 32, Watts, Strogatz 33, and Barbarossi, Albert 34, to match the graph density, D equals, of each estimated connectome and ran the same count of subgraph motifs on samples taken from each random graph distribution. These models were chosen for their simplicity and small parameter spaces. We similarly performed the same subgraph motif counts on the configuration model, XSwap 35, a degree-preserving graph randomizer used in previous neuroscience efforts 10. Unlike the other models, this model begins with an existing connectome graph and performs arbitrary swaps of edges such that the overall in and out degrees of each node remains the same, but the precise pattern of connectivity changes 36. Because the X-swap procedure preserves the degree sequence of its source network, random permutations generated in this manner closely mirror the motif counts of the original source connectomes. More details about the random graphs used here are available in Methods. The graph densities were set to 0.03 for the microns graph and 0.06 for the C. elegans graph. Table 1. In order to compare these results with a complete connectome example dataset, we ran this count scan on all chemical synapses of the hermaphrodite C. elegans connectome 24, 25, 27, 37 available from worm wiring, org 24. All motifs tested occurred at least once in the C. elegans connectome. We discovered that the motifs encountered most frequently in one connectome tended to be the most frequent in other connectomes and their random graph counterparts, but the absolute counts of each motif differed dramatically based upon the connectome and motif in question. Figure 3. Figure 3. Undirected motif searches, monomorphisms, in connectomes and random graphs. A. B. The count of every undirected subgraph with 6 or fewer vertices. Each motif was counted in the connectomes, as well as in each of the random graph models calibrated to match the density of each connectome. The x-axis is the motif ID from the Atlas of Graphs text, e.g. all points on the line represent the undirected triangle motif. Gaps along the x-axis indicate omitted motifs, i.e., those with multiple connected components. A. Comparing C. elegans with random graphs calibrated to C. elegans density. Due to its higher density, the C. elegans graph has higher motif counts than those of the microns graph, despite a lower vertex count. X-swap motif counts, blue, closely match those of the original connectome, black. In contrast, Erdos, Reilly approximations, yellow, are very poor predictors of true connectome motif count and always underestimate motif counts in the original connectome. The parameter space of the Watts, Strogatz model, red, leads to a wide range of motif count predictions, some as low as those of the Erdos, Reilly model. B. Comparing microns with random graphs calibrated to microns density. Like the C, elegans results in A. Erdos. Reilly approximations always underestimate the number of motifs for all motif graphs we searched. The same motifs, etc., occur with the highest frequency in the microns graph as in the C. elegans graph. Motif, the fully connected graph on 6 nodes, appears many thousands of times in the C. elegans graph, but does not occur at all in the microns connectome. Some models, like X-swap and Erdos, Reilly, likewise predict 0 motif occurrences. Others, like the geometric model, green, erroneously over-predict the number of expected subgraphs. Full-resolution copies of this graphic are available online. See Supplemental Material 1. Full-size image. Directed 3-node motif searches in microns and C. elegans. Recent work has investigated the relative prevalence of directed 3-node motifs in brain graphs and the importance of such motifs for local computation 10, 38, 39, 40. Here we count all unique, directed 3-node motifs in the microns phase 1 and C, elegans connectomes. Lower density 3-node motifs appeared with greater frequency due to the larger number of embeddable permutations. Despite similar neuron counts, the connectomes differed dramatically in both absolute count and distribution shape, with many directed motifs occurring frequently in the C, elegans graph, but few to no times in the microns graph. Figure 4. Figure 4. Quantities, monomorphisms, of directed 3-node motifs from the C, elegans chemical synapse connectome and the microns V185 graph. A, C, elegans directed 3-node motif counts. The most commonly encountered directed 3-node motif is the fan-in motif, where two neurons converge to a single downstream target. All directed 3-node motifs occur at least once. B. Microns V185 directed 3-node motif counts. The most common motif is the fan-out motif, where one neuron synapses onto two downstream targets. Several 3-node motifs appear infrequently or do not appear at all. This illustrates differences between the connectivity patterns of a complete connectome, such as the worms and a mammalian brain region that is expected to be largely feed-forward. Full-size image. These simple motifs serve as a useful frame for further investigations. Though there are only 13 3-node directed graphs, exhaustively searching for all larger directed motifs quickly becomes computationally infeasible. There are 199 connected 4-node directed graphs, 9,364 connected 5-node directed graphs, and over 1.5 million connected 6-node directed graphs. It is possible now to search specifically for larger supergraphs of only motifs, which occur at least once in this study, greatly reducing the search space of future exhaustive motif searches in these connectomes. Unlike the distributions of undirected motifs, the relative distribution of these directed motifs does not appear to follow a consistent shape between connectomes. This suggests that even these small motifs may hold useful knowledge about the nature of connectome graphs, such as distinguishing between feed-forward dominated or feedback-dominated tissue. Benchmarks. Figure 5. Comparison of wall clock runtime when counting undirected motifs. All runtimes are measured during motif searches in Erdos. Reilly graphs with node count sampled uniformly on the interval of 100 to 300 nodes, and with densities randomly sampled between 0 and 0.3. See benchmarks for more details. Here, we compare performance on a variety of motifs, such as the 3-node path graph, the 4-node cycle graph, and complete cliques of various sizes. Full-size image. Users may find that different DotMotif executors suit the needs of different research questions. In order to illustrate these differences, we compared the performance of 3 DotMotif executors available for use in our downloadable Python module. The Grand ISO executor and NetworkX executor are both pure Python and are therefore desirable for use in constrained compute environments such as shared servers. The Neo4j executor requires a Neo4j database, which runs as a standalone executable. Figure 5 illustrates that the novel Grand ISO-based executor developed under this effort always outperforms the NetworkX executor, regardless of host graph size and motif. Due to the additional overhead time spent provisioning Neo4j databases, we do not compare these much longer-running results here. Though we compare searches for small, undirected motifs in Erdos, Reilly graphs in Figure 5, the Grand ISO search outperformed NetworkX VF2 on the exhaustive connectome motif searches in Figures 3 and 4. All graphs were generated using the NetworkX fast_GNP_random_graph algorithm with graph sizes uniformly sampled between 100 and 300, with densities uniformly sampled between 0.05 and 0.3. Complete results are available in Supplemental Material 1. When choosing between Python-based and graph database executors, there is a trade-off between data ingest rate and search speed. The NetworkX executor and Grand ISO executor, which convert DotMotif DSL syntax into a series of Python commands, are preferable for running graph queries on a small host graph or for running the same queries on many host graphs, due to low startup time overhead. The Neo4j executor, which converts DotMotif DSL syntax into a cipher query for execution with the Neo4j graph database, has significant data ingest overhead for the first query on a graph, and so it is not ideal for running individual motif queries. However, users may prefer a Neo4j executor when running multiple queries on the same host graph when many users are running motif queries simultaneously on the same host, or if motif searches are likely to be repeated. For queries on host graphs of sufficiently large size, the Neo4j executor. Startup overhead becomes trivial compared to the total runtime of the query, and for larger-than-memory host graphs, the Neo4j executor and newprint executors may be the only feasible options. For most in-memory exploratory data analysis, we recommend the use of the Grand ISO executor. DotMotif users may trivially switch between executors without modifying their queries, as the DotMotif engine stores queries in an intermediate format after parsing and validation steps. Figure 6. Figure 6. The DotMotif query execution process. Graph import. A user may import a search graph, also commonly referred to as a host graph, from a variety of industry standard formats, including an edgelist CSV, GraphML, NumPy adjacency matrix, and any format supported by the NetworkX library. Furthermore, DotMotif is compatible with graphs stored in newprint schemas in a Neo4j database 6. Query design. The user may select from a library of pre-built motifs or write a novel query. The query may be written in the DotMotif DSL, encoded as a NetworkX graph, or written as text directly in the target graph database query language, such as Cipher. A user may choose to save this query as another standalone file on disk for future use. The DotMotif file format stores both the motif itself and provenance metadata, such as the date of creation, comments associated with the motif, and author information. Query validation. DotMotif supports several pre-execution validation steps in order to fail quickly when asked to perform an impossible or self-contradictory query. Several other optional validators may be invoked to check a motif for biological feasibility and to warn the user if a potential error is detected. Execution and results. The user may choose from the available DotMotif executors in order to use the most appropriate subgraph matching tool for the compute resources available. No further query modification is required in order to run the same motif on several different executors. A user may also choose to simply use DotMotif as a query executor without leveraging the query validation or query design tools. Full-size image. Methods. In developing DotMotif, we aim to ensure that our software was both accessible, intuitive for new users, but powerful enough for power users, as well as sufficiently computationally efficient to execute most common queries on commodity hardware. In the interest of research flexibility, we also required that the software adapt to best utilize available hardware resources. For this reason, DotMotif includes several executors, each of which leverage a different graph analysis technology. Executors are discussed in greater depth in the benchmark section. Formal definition of the subgraph search task. Here we consider the ideas of subgraph isomorphism and subgraph monomorphism, which have slightly varying definitions in the graph theory literature. When we refer to a subgraph, we always refer to a node-induced subgraph, which is in line with the usage in popular subgraph isomorphism research, including research on the commonly used VF2 algorithm 41, 42, 43, given graphs, and we say G is isomorphic to H if there exists a bijection such that if and only if 44. An extension of this idea is that a subgraph isomorphism exists between G and H if and only if there exists a subgraph of G such that is isomorphic to H. A monomorphism loosens the bijection requirement to simply injection, meaning that the match in the host graph may contain extra edges. DotMotif finds all subgraphs in a search graph that match a query graph, where the term match used here means that one of the above described mappings exists. By default, DotMotif will perform a search for all subgraphs that are monomorphic to the query subgraph. A user may choose to search for exact matches only, in which case DotMotif identifies subgraph isomorphisms rather than monomorphisms. This behavior is controlled by a user toggle during the construction of a query. Optimizations to the subgraph isomorphism task in Python. For the purposes of quick iteration upon neuroscience hypotheses, our team required a high-speed subgraph isomorphism algorithm that was both pure Python in order to reduce the barrier to entry for a fresh installation, as well as optimize to minimize CPU and memory usage. To satisfy this need, we developed a subgraph monomorphism search implementation that performs favorably against the standard NetworkX implementation, Figure 5. Our pure Python implementation matches the results of the NetworkX Graph Matcher monomorphism detection module with significantly lower CPU and memory overhead. Additionally, while many modern subgraph ISO and monomorphism implementations rely on a directed, acyclic graph state space representation, our implementation stores its state space in a one-dimensional queue, algorithm 1. In future work, we expect that due to this property, our algorithm may be trivially parallelized to operate on multiple cores at once. Optimized interfaces for common graph libraries. Many existing research questions have been explored with RAM-sized graphs in mind and have utilized popular Python graph libraries such as NetworkX or iGraph 1945 or emerging libraries such as Networkit 46. In order to easily transition these algorithms and analyses to graphs of larger size, we developed an open-source graph library that enables a user to write code using familiar graph APIs, e.g. NetworkX's nnext, digraph, but which automatically converts these commands to run instead on any of a number of optimized, scalable backends, such as a graph database implemented in SQL or Amazon Web Services DynamoDB. This tool, alongside the subgraph ISO and monomorphism improvements detailed above, enabled us to achieve substantial performance speedups in performing the analyses in this paper. Links to documentation and the source code for this library are available in Supplemental Material 1. All benchmarks listed here were performed on consumer laptop hardware with 16 GB of RAM and a 3.1 GHz Intel Core i7 processor. Comparison to random graph models. One way to determine if a motif is significant within a real biological dataset is to compare its observed frequency to its expected frequency within a random graph model. There are many different random graph models, each with different properties and capturing a different aspect of real-world data 47. Here, we perform subgraph search on 5 different random graph models. The Erdos. Any random model has parameters n, or the number of nodes, and p, or the probability that any of the potential edges will independently exist within the graph 31. The Erdos. Any model is easy to analyze and understand, and thus is included in this analysis. However, the edge independence assumption often fails for real datasets. Thus, other models are required to provide further context. Geometric random graphs are desirable because they naturally capture spatial relationships that occur within the brain 48. Nodes are uniformly distributed within a region and 2 nodes are adjacent if they fall within a radius r, which is an adjustable parameter 32. This model, however, does not capture long-range neural connections, resulting in some spatial relationships that are not captured by the point cloud approach of the geometric model. The Watts-Strogatz model addresses the edge dependence issue more directly, recognizing that many real-world networks have high clustering coefficients, which is a measure of the extent to which 2 adjacent nodes have similar neighbors 33. The Barabasi Albert model is a preferential attachment model that ensures a power law degree distribution, making it a scale-free graph model 3447. The degree-preserving edge randomization graph model implemented here, based upon efforts such as those in Refs. 3649, accepts a graph as input parameter and performs edge swaps between two randomly selected edges, and so that the resulting edges are and. This model preserves the in and out degree distribution, as well as the in-degree sequence. Here, this model serves as a control in order to determine the role of degree distribution when determining the prevalence of a motif. Each of the described random models has a set of parameters resulting in different graph properties. These parameters may be selected to generate graphs similar to the real dataset in question. Similarity can mean different things, and we try to match the models to a characteristic that is closely tied to motif search. One obvious choice is to match the graph density, D smiley face, of each estimated connectome, because density is a metric that can be more easily tweaked across models. Furthermore, a density that is too high or too low can result in inflated or underestimated subgraph counts, respectively 50. Other metrics besides graph density may be considered, such as the degree distribution. Regardless of the metric, the parameters selected for a random graph model will differ for each connectome being analyzed. More specifically, differences in density for C, elegans, and microns datasets will result in differently parametrized random graph models. By performing subgraph search across these models tuned or calibrated to some characteristic of the real dataset, we narrow the problem space of what drives a given motif to occur at a given frequency. By understanding which models closely approximate certain phenomena, such as motif count, we may be able to better identify biological mechanisms that induce these patterns of connectivity in the connectome. Architecture. DotMotif is comprised of three submodules: a parser module, an optimizer module, and finally an executor module. In order of use, the parser module is responsible for converting the DotMotif domain-specific language into an in-memory representation. The optimizer module is then responsible for converting and simplifying the in-memory motif into its simplest possible representation. The optimizer module may also optionally check for violations of biological priors in a validation step. Finally, the executor module converts the optimized motif into a query that can be submitted to a graph analysis tool. Each executor is responsible for generating its own target-specific queries. For example, the Neo4j executor generates cipher queries, and the NetworkX executor converts queries to a sequence of Python commands. Through the coordination of these submodules, DotMotif provides a framework for posing and answering complex graph queries. DotMotif domain-specific language parser. We identified an impedance mismatch between the flexibility of common query languages, such as Cipher7, and the needs of the research community, where many research questions require overwhelmingly complex or verbose queries. We opted to develop a domain-specific query language to aid in the construction of queries. This enables research-driven query design agnostic to the underlying frameworks. The DotMotif domain-specific language, DSL, borrows from DOT-like syntax 51 as well as from SQL-like syntax in order to expose a succinct and user-friendly query language. For example, the simple query A-B will return a list of all edges in the complete graph. In other words, the list of all subgraphs of that comprise one edge from a node to node. In order to make queries understandable and maintainable, the DotMotif DSL supports macros or composable building blocks that can be combined to generate more complicated queries, Figure 2c. These macros minimize boilerplate syntax without leading to duplicate notation, Figure 2d. Further illustrations of the DotMotif DSL syntax are available in Fig. 7a, Figure 7. Examples of the DotMotif query language. A. Features of the DotMotif domain-specific language syntax. Nodes are connected by directed edges, notated with an arrow operator. A user can specify whether a certain edge must not exist by using the non-edge operator. Both edges as well as nodes may be assigned constraints or attributes. Edge attributes are nested in square brackets on the same line as the edge notation, and node attributes are notated with dot notation on their own line. A user can explicitly indicate that two nodes are interchangeable, and DotMotif will only return one representative of that automorphism group. B. Example use of nested macros to construct a complex motif from simple building blocks. In this motif example, x, y, and z serve as macro arguments. These variables, similar to local function arguments in other programming languages, are only used within the macro and are not participants in the motif. Nodes with names AE serve as participants in the motif. Note that macros may be nested by calling one from within the body of another. See examples of motifs that fail validation. The DotMotif query validation step reduces the likelihood of spending computational resources on impossible or biologically unfeasible queries. In the first example, validation fails because an edge has already been added to the motif, but a new line, red underline, conflicts with this requirement. In the second example, validation fails because the condition is impossible. No value for A size can be both greater than 50 as well as less than or equal to 5. These validation failures serve as early warning signs for a researcher to see that a query will fail if executed. Full-size image. By default, DotMotif returns a single representative element of each automorphism group in the result set. An automorphism is an isomorphism from a graph onto itself 44. Returning a single representative of the automorphism group avoids overcounting motifs in the search graph due to motif symmetries. The ability to count only one representative of this group is useful to many common neuroscience questions, but it is not easily accomplished with conventional graph tools. A DotMotif user may also explicitly specify that two nodes in a motif are interchangeable with the automorphism operator, figure 7a. Whether the user uses automatic query automorphism detection or notates it manually, the DotMotif optimizer will enrich the query motif to lower the space of possible matches and thus return a result more rapidly. DotMotif considers both semantic as well as syntactic feasibility when automatically determining automorphism mappings 42. This language is formally defined in extended Bacchus, Nauer Form 52, 53 by the grammar file referenced in Supplemental Material 1. This syntax is visualized using the railroad diagram convention in Figure 8. Figure 8. The DotMotif syntax in railroad diagram form. The DotMotif DSL is a whitespace agnostic language with hash symbol comments and curly brace bracketed macros. Edges are defined with dash arrow-like syntax. Edge attributes may be listed in JSON-like syntax. Node attributes may be listed in object.notation syntax. For example usage of this syntax system, refer to architecture. This syntax is formally defined in extended Bacchus-Nauer form. Both this formal definition as well as the language specification will be made available as per Supplemental Material 1. This figure was generated with the Railroad Diagrams node, JS Package 77. Full-size image. Query optimization and validation. After a query has been parsed and ingested, it is passed to an optimization stage in which the query is reduced to a simplified form in order to improve the speed of query execution. Optionally, a user may also enable the automatic detection of impossible structures or even biologically implausible structures in a validation step, Figure 7c. These verbose error messages are intended to warn a user quickly and clearly if a graph query is unlikely or impossible, rather than allowing the user to proceed with a long-running query that is destined to fail. In contrast, the equivalent cipher command running in Neo4j will still go through the process of execution on the full host graph, but will return no results. DotMotif includes the option to add validators for biological plausibility. These options allow the user to prohibit motifs that, for example, require inhibition and excitation to be performed by the same neuron. These validators, like all validators in the DotMotif package, are both optional as well as modifiable. Query execution. A parsed, optimized, and validated query can now be evaluated against a large graph. Where necessary, it is possible to run these queries fully in memory on consumer hardware. DotMotif includes both pure Python as well as graph database query executors. There is no difference between the results returned from each executor, and so they may be used interchangeably, depending upon the needs and parameters of the experiments and environments. In order to take advantage of graph database technology, we have implemented a Neo4j executor, which leverages the Neo4j7 database and its built-in subgraph match detection algorithm, an implementation of the VF2 algorithm 42. In order to run queries in this environment, our software converts the optimized query to Cipher, the database query language used natively by Neo4j. If a user does not have a running Neo4j database, our library also includes routines to provision a Docker container 54 and quickly ingest the data in an appropriate format for Neo4j to use. A user may also direct queries to a running Newprint database 6. A list of all available executors is available in Table 2.
Table 2: a comparison of DotMotif executors. Full-size table. Discussion. Though modern connectomics research commonly interprets neural connectivity as a network, the field currently suffers from a lack of accessible, performant graph analysis and subgraph search tools. In this work, we present DotMotif, a combined domain-specific language and interface to powerful graph search tools. Our hope is that this tool and others like it will reduce the barrier to entry for researchers unacquainted with graph theory or graph databases, and will enable researchers to interrogate increasingly common connectome datasets with ease. Though the indirect graphs from the Graph Atlas study may not directly provide answers to open questions in neuroscience, this broad search can narrow down where it may be most impactful to dig deeper, perhaps leading to more interesting directed graph searches or neural simulations over smaller directed versions 55. Such exhaustive motif searches may also enable better characterization of local network properties and dynamics 39. Future work may include random assignment of edge direction in order to perform an unbiased search across the space of all possible directed graphs, akin to other random graph searches. 8. We intend to further explore other metrics beyond density for random graph model calibration in the future. Through these directed and indirect motif studies, it may also be possible to build a heuristic to predict motif counts in a connectome using a small number of simpler, i.e. lower computational cost, motif searches, and avoid explicit counting altogether. For example, if the goal of a research study were to determine if the actual count of a motif in question aligns with predictions for a connectome of a certain modality, size, species, and brain region, such a model would circumvent the need to search in random graph models, and would instead enable a simpler, analytic approach. Recent neuroscience research 10,1238,56,57 has provided many valuable explanations for neuron-to-neuron connectivity rules. We intend for these tools to offer a quantitative way to expand these rules to larger numbers of neurons, and to free the neuroscience community to explore new questions in the connectomics domain. Similarly, several efforts have begun to map subneuron connectivity patterns, identifying recurring motifs in the relationships of multiple synapses between the same neurons 58, 59, 60. We believe that the systems presented here will provide a substrate upon which to build not only nanoscale connectivity research but also subcellular motif work and meso to macroscale connectomics, through modalities such as X-ray microtomography or MRI 18, 61, 62, by identifying motifs in network connectivity across brain regions or in large-gauge neurites 63, 64, 65. Despite many of the simplifications and optimizations to the subgraph monomorphism task mentioned here, this task in general is NP complete 43, 66, 67, 68. Even in a relatively small connectome such as that of C. elegans, certain sufficiently common or poorly optimized motif searches may still remain infeasible to run on consumer hardware. In our experience, the addition of further constraints, such as specifying edge direction, specifying node and edge attributes, or searching for query graphs with nodes of high degree, may reduce the execution time of complex queries, but other seemingly helpful modifications, such as increasing the diameter of a query graph, may counterintuitively increase runtime quite substantially. As a result of such longer query runtimes or more compute-hungry queries, researchers will be able to run fewer queries per study.
In our ongoing work, we hope to reduce this barrier by developing more rigorous automated query optimizations and by publishing connectome query results for reuse. We also hope to use tools from probabilistic and Bayesian network analysis to better understand how global network properties, such as degree sequence or density, impact motif incidence. We will introduce and refine new validators that aid DotMotif query designers in identifying qualities of a query graph that may lead to long runtimes. And we hope that the Atlas results published above may shed light on how to select query graphs for further study in a dataset. We intend to disseminate an open data motif encyclopedia so that long-running or complex queries may be run on a dataset once and then shared with the community. We also note that faster implementations of the motif search problem, relevant to connectomics, pharmaceutical research, and other domains, may pave the way to faster and more efficient scientific discovery. The field of connectomics is at an inflection point as datasets continue to grow in size. As technology and neuroscience provide avenues to create and study large datasets at unprecedented scales beyond the analysis capabilities of a single lab. Open, free, and public datasets, as well as accessible and affordable tools to understand those public data, are of paramount importance. We are releasing the DotMotif codebase, as well as all demonstration code and data in this manuscript, as open source and open data tools to support community discovery. We invite collaborators to share questions that allow us extend DotMotif to test scientific hypotheses. Citation Diversity Statement. Recent work in several fields of science has identified a bias in citation practices such that papers from women and other minority scholars are undercited relative to the number of such papers in the field 69, 70, 71, 72, 73. Here we sought to proactively consider choosing references that reflect the diversity of the field in thought, form of contribution, gender, race, ethnicity, and other factors. First, we obtained the predicted gender of the first and last author of each reference by using databases that store the probability of a first name being carried by a woman 73, 74. By this measure, and excluding self-citations to the first and last authors of our current paper, our references contain 7.94% woman, first/woman, last, 14.29% man/woman, 22.22% woman/man, and 55.56% man/man. This method is limited in that A, names, pronouns, and social media profiles used to construct the databases may not, in every case, be indicative of gender identity, and B, it cannot account for intersex, non-binary, or transgender people. Second, we obtained predicted racial/ethnic category of the first and last author of each reference by databases that store the probability of a first and last name being carried by an author of color. 75, 76. By this measure, and excluding self-citations, our references contain 6.33% author of color, first/author of color, last, 31.65% white author/author of color, 13.92% author of color/white author, and 48.1% white author/white author. This method is limited in that A, names and Florida voter data to make the predictions may not be indicative of racial/ethnic identity, and B, it cannot account for indigenous and mixed-race authors. or those who may face differential biases due to the ambiguous racialization or ethnicization of their names. We look forward to future work that could help us to better understand how to support equitable practices in science. References: Bassett D. S., CERN P., and Gold J. I. On the Nature and Use of Models in Network Neuroscience. Nat Reverend Neurosci. 566 to 578. https://doi.org/1038-1038-018-038-8 2018. Article SAS PubMed Central Google Scholar. Su C. S. et al. A connectome of the adult Drosophila central brain. Via zips //doi.org/10.1101/2020.01.21.911859 2020. Article PubMed Central Google Scholar. Vogelstein J. T. et al. A community-developed open-source computational ecosystem for big neurodata. Nat Methods. 846 to 847. https://doi.org/1038-018-018-1 2018. Hocevar T. and Demsar J. Combinatorial Algorithm for Counting Small Induced Graphs and Orbits. PLOS 112, E017148. https://doi.org/101371/journal.pwn 0171428 2017. Article SAS PubMed Central Google Scholar. Sheffer L. K. Graph Properties of the Adult Drosophila Central Brain. Via zips //forward/10.1101/2020.05.18.102061 2020. Article Google Scholar. Clements J. et al. New print. Analysis Tools for EM Connectomics. Via zips //forward/forward/doi.org/10.1101/2020.09116.9094665 2020. Article PubMed Central Google Scholar. Fernandez D. and Bernardino J. Graph Databases Comparison. Allegro Graph, ArangoDB, Infinite Graph, Neo4j, and OrientDB. Data 20, 373 to 380, 2018. Google Scholar. Sporns, O. and Cotter are motifs in brain networks. PLOS Biol, 369, 20, 2004. Google Scholar. Mountcastle, V. B. Modality and topographic properties of single neurons of cat's somatic sensory cortex. J. Neurophysiol. 20, 408 to 434. https://doi.org/10.1152/jn.1957 20.4.408 1957. Article SAS PubMed Google Scholar. Turner N. L. et al. Multiscale and multimodal reconstruction of cortical structure and function. Via zips //forward/doi.org/10.1101/2020.10.14.338681 2020. Article PubMed Central Google Scholar. Schreiber F. and Schwabermeyer H. M.A. Visto, a tool for the exploration of network motifs. Bioinformatics 21, 3572 to 3574. https://doi.org/1093/BTI556-2005. Article SAS PubMed Google Scholar. Milo, R. et al. Network motifs. Simple building blocks of complex networks. Science 298, 824 to 827. https://doi.org/1038-018-038-0038-80, 2002. Article adds SAS PubMed Google Scholar. Pospelov, N. et al. Spectral peculiarity and criticality of a human connectome. Phys. Life Rev 31, 240 to 256. https://doi.org/1038-018-0038-81, 2019. Article adds SAS PubMed Google Scholar. Reilly, E. P. et al. Neural Reconstruction Integrity, a metric for assessing the connectivity accuracy of reconstructed neural networks. Front. Neuroinform. 1274, 2018. Article Google Scholar. Reilly, E. P. et al. Connecting Neural Reconstruction Integrity, NRI, to graph metrics and biological priors. In Complex Networks 11-182 to 193, Springer, 2020. Chapter Google Scholar. Sporns, O. Structure and Function of Complex Brain Networks. Dialogues Clin, Neurosci. 15, 247 to 262, 2013. Article Google Scholar. Swanson, L. W. and Lichtman, J. W. From Cahal to Connectome and Beyond. Anna, Reverend Neurosci. 39, 197 to 216. https://doi.org/1038-018-0038-0038-82, 2016. Article SAS PubMed Google Scholar. Bassett, D. S. and Sporns, O. Network Neuroscience. Nat Neurosci. 20, 353 to 364. https://doi.org/1038/S41583-018-0038-2